In this video lecture, we will solve what's known as an arc length problem. And first, let's discuss what is the arc length problem. Arc length problem is us being interested in finding the length of a piece of some function on the interval between a and b. So for example, this can represent a path of an object in two-dimensional plane, and we may want to know the length of the path. And we do know the solution of this problem for some simple curves. So for example, if I give you a circle of radius 1 and let's say we define this function as the upper half of the circle centered at 1, 0, and we do know the length of this path. It will be exactly pi. And we also know the solution of the arc length problem for some other simple curves such as line. So let's say if we go from 3 to 7 and from 4 to 6. So let's say we have this line segment. Here's a little pop quiz for you. Pause the video and tell me what is the equation of this line. Well, the slope is 1/2, and when x is 3, we get 4, so 3/2, so it's 1/2 x plus 1/2. Let's try. So when x is 7, we should be getting 6 7/2. No, we're not getting that. So then 3/2 plus, I think this should be 3/2. Let's try again. Nope. So this should be 5/2. There you go. Now plug in x equals 3, we get 4. Plug in x equals 7, we get 6. Awesome. And to find, we actually don't have to do anything other than the Pythagorean theorem to compute the length of this path. It will be the square root of, and here we have, this is 4, this is 2, so it's going to be square root of 4 squared plus 2 squared, which is square root of 20, which is 2 radical 5. So as you can tell, we do know the solution for some curves, but not all. And before we build up our skills, let's kind of try and generalize the straight line path problem. So can we do this problem in general? So let's say if we have, what do we need to know about a line segment to be able to compute the length of this line segment? And turns out that it is sufficient for us to know just the change in the x-coordinate and the slope. So if somehow you know the slope and the change in x-coordinate, then you can find the length of this, what appears to be a hypotenuse of a right triangle. And how do we do that? So well, we're going to do it in 2 steps, right? So delta y is equal to the slope times delta x, and then the L, which will abbreviate this length, will then be equal to delta x squared plus delta y squared, but delta y is like in our previous problem, delta x was 2, delta x was 4, m was 1/2. So when we plugged everything in, we ended up with we ended up with 4 squared plus 2 squared, which is what we got, 2 vertical 5. And in order for us to continue building this skill, let's also recall from Calculus 1 the mean value theorem for derivatives. There is a mean value theorem for integrals, but let's recall the mean value theorem for derivatives. And it says that if you have a continuous function, differentiable, I guess it's sufficient to say differentiable, differentiable functions are continuous on some interval from a to b. What does the mean value theorem tells us? Again, make it another pop quiz, pause the video, try to recall what the mean value theorem says, and unpause when you're ready. So the mean value theorem says that there exists some value c on the interval from a to b, and let's make it inside of the interval, such that the derivative of the function at c is exactly the same as this. So geometrically, what does this mean? Well, fb minus fa over b minus a is called the difference quotient, and it represents the slope of this secant line, and f prime of c represents the slope of the tangent line at point c. So basically it guarantees that under certain conditions there exists at least one such c where the slope of the tangent line at that point is exactly the same as the slope of the secant line of the secant line segment that connects the endpoints of this graph. So this is what the mean value theorem for derivatives tells us. And now we are ready to solve the arc length problem. So let's start. Let's draw out some generic curve, and we're going to start here at A, we're going to end here at B, and again the goal is to find the length of this curve. The first thing we're going to do is we're going to divide the interval from A to B into a partition that is into n subintervals equally spread out. They don't have to be equally spread out, but having them equally spread out makes things a little bit easier. But in theory it doesn't have to be. As long as the largest one goes to 0, then we would be fine. But like I said, it just makes things easier to have them equally spread out. And this partition, or any such partition, will create points on the curve. So let's label these points as P0, P1, P2. The last one would be Pn, Pn minus 1, Pn minus 2, and these two will be Pi minus 1, and Pi. And the goal is to find the length of the curve, but we're going to approximate that length with the sum of individual lengths. So we're going to send I from 1 to n, and the total length will be equal to the sum of the lengths of each of those line segments. And let's focus on one of this. So let's just take a look at the ith segment, and let me highlight it with a different color. So we have something like this going on here. So right here. So this right here represents this curve represents that one segment. And let's see what we can do here with, can we try to find a formula to find the length of that one line segment? Well, the smaller the distance between the two axes, the more that segment look like a straight line segment, and therefore we can approximate the length of that line segment. Well, we can approximate the length of that segment with the length of the line segment, which is a straight line. So if we zoom in and look closer into what's happening between xi minus 1 and xi, let's say we're going to see something like this. Then we can introduce the following notation, right? So as always, we're going to have n subintervals, and delta x will be the width of each one, which can be found using this formula. And on this picture, delta x will be right over here. And if we temporarily label this as delta y, then the length of this orange segment can be approximated with the length of this hypotenuse. And now we just need to find a way to relate, have as least amount of variables as possible, or as least number of moving pieces as possible. So what we're going to do is we're going to identify the slope of this line right here, So if we, for example, knew this is m, then we would be able to set delta y equal to m times delta x. And then in that case, this line segment will be approximated, like its length would be approximated by this expression. It will be delta x squared plus m delta y, m delta x squared. At first sight, this m has nothing to do with delta x, and it almost looks like we are stuck here. I'm just going to add index I over there. But if we use the mean value theorem for derivatives, then it guarantees that there exists c on the interval xi minus 1 xi such that the derivative of the function at that point is equal to but this is exactly our m. And I guess I shouldn't be using b and a here. I should be using xi minus 1. And now we're just going to not call it c, but we're going to call it xi star. So the mean value theorem guarantees the existence of such number, and if it exists, we are going to pick that value as a representative for that particular interval. So in this case, we'll just pick xi star here, and then at this point, the slope will be equal to that I. Now, what does that mean? Well, that means now that we don't just have mi, we have this following expression here. Instead of mi, we would put f prime of xi star, and we would square it. And now we can treat this delta x as a variable or as a constant, and we can take it outside of this radical. So what just happened is that we said that for each interval, or in particular we looked at the ith interval over here. So we look at the ith interval. On that interval there exists xi star, the derivative at which is equal to the slope of the line, of the secant line, and therefore the line segment can be approximated with this formula. So let's just write that out. So we approximate the length of this line with this formula. And let's put it all together. We just learned the arc length of ith segment can be expressed like this. But we have n such segments, so let's put it together. So arc length of n segments can be expressed with the sum and if we increase the number of segments to be very large, then the length of all of those segments together will be expressed like this. And now we need to look at it carefully and recognize something. This totally looks like a Riemann sum, and therefore this limit can be expressed as an integral as a definite integral. And this is what we are going to call the arc-length formula. So if such limit exists, then it's equal to that integral. So if arc length exists, we can find it by computing this integral. So let's practice using this formula. When we use this formula, we don't just rush into computing everything. We do it in steps or increments. So the first step should be, you don't even have to set up the formula right away. The first step should be to find the derivative. You don't want to set up the formula and only then start looking for the derivative. Find the derivative first. In the second step, you want to do all this algebraic manipulations. So you want to, after you found your derivative, you want to square it, you want to add 1 to it, you want to take the square root, and you want to take all that, and you want to make sure that it is simplified. And after you simplify that, only then I would suggest you set up the integral. So let's go ahead and do an example of that. We'll follow this exact steps. So let's find the arc length of a piece of this function on the interval from -1 to 1. And we know we're going to be using this formula, so in your mind you can start thinking of this formula. You should be thinking about this formula, but we can just find this integral. So we're going to hit the pause button here and we're going to do it in steps. Step 1, we're going to find the derivative of this function. So 1/2 radical 1 minus x squared multiplied by the derivative of what's inside, -2x, and I'm going to simplify it as much as I can. Step 2, I'm going to compute this expression or rather simplify, not compute, and let's do it. So we haven't even done any calculus here yet, we just well, we did some calculus 1, but we haven't done any calculus 2 stuff yet. So now to simplify it, it's just pure algebra. We're going to have to do some simplification here. We're going to have to find the common denominator. And after all of that, we see we have 1 minus x squared plus x squared. And looks like it simplifies to this. Isn't that great? And only now we're going to unpause our solution so we can hit the play button in our solution and continue. So now we're going to set up this integral from -1 to 1 of 1 over 1 minus x squared dx. So this is a standard table integral, so it's the arcsine function from -1 to 1, and we got arcsine of 1 minus arcsine of -1, which is pi. So actually we can check our work. What we had was the equation of the upper half of the unit circle. So of course the arc length of it is pi. But we tested and practiced the arc length formula, which was the purpose. Let's do another easy problem just to get used to the process. Let's find the arc length of the following function. And on the interval from 3 to 7. And we're going to be using the same formula, so I'm not going to even write it out. I'm just going to start doing the steps. The first step is to find the derivative. The second step is to plug it in here and simplify. And step 3 is to actually integrate. Well, it's a simple integral. And we're just gonna simplify it, right? So this is that, and here we have 7 minus 3. So the final answer is 2 radical 5. So if you remember, this is that same problem that we did earlier. So hopefully now we built enough trust into this formula, and let's do more exercises. Let's find the arc length of this power function on the interval from 0 to 1. Step 1, differentiate. Step 2, simplify this expression. Like, you don't want to do this algebra stuff inside of the integral. You want to simplify it first and then put it inside of the integral. So here we have this function, and now we're setting up the integral from 0 to 1, and we're integrating this. Now, by now you should know which integrals are possible and which integrals are impossible to do by hand. So this is one of those integrals that it's probably not possible to do it by hand. So we're either going to use numerical integration that is, we would just use a Simpson's rule or something like that, or we can simply use technology. So whichever way you prefer, I'm just going to go open Wolfram Alpha. And I'm going to type this problem. And we have a square root of 1 plus 16x to the power 6. And it seems like the answer is 1.6 units. We're looking for the arc length here, so whatever units are, those would be the units of the arc length. Now I want to show you an example of a special pattern that frequently shows up on problems like this on the homework and exams. It's just one pattern. So you want to be able to recognize it so you don't end up wasting time. So all these problems kind of have distinct look, and when you see a problem like that, again, like I said, you want to be able to recognize the pattern. So step 1, let's take the derivative. 4x cubed over 8 plus, probably minus, we're going to have negative 2 over 4x cubed. And we're going to simplify it a little more, right? So we're going to have x cubed over 2 minus 1 over 2x cubed. And now we're going to create an expression like this, but we're going to do it in steps. So we're going to do it even slower. First, we're going to square this. And to square this, I'm going to use this formula. So to square difference of two numbers, we square the first, subtract 2 times the product, and then add square of the second one. So this will be x cubed over 2 squared minus 2 times the product will be 2 times the product and plus we're going to have this squared. And now we're going to be noticing something very interesting. So in the middle we end up with just 1/2. So the whole middle part just equals to 1/2. So what does that mean? That means when I add 1 to the f prime squared, well, that negative 1/2 will turn into positive 1/2. So I want to just write this out carefully here. Just want to make sure you see this pattern. So basically we're going to end up with the same exact expression, but instead of minus 1/2, we're going to have positive 1/2. And so what, you may ask? Well, let's recall that there are two formulas for squaring, and the difference between them is exactly in the sign of the middle term. So when you have the same exact thing, but instead of minus you have plus, what you actually have is the square of x cubed over 2 plus 1 over 2x cubed. So that means when we throw the square root on top, the square root and the square, we can cancel them because everything is positive, and we end up with a simple expression again. So the whole idea here was to exploit this pattern, and once you do, you end up with a very simple integral from 1 to 2, and it's just a power function which should be easy to integrate. So for this one, we probably don't need technology. We have 1/8 x to the 4. And here we're going to have minus 1 over 4x squared, which should look familiar, and we evaluate all that between 1 and 2. So when we plug in 2, we end up with just 2 minus 1/16, and when we plug in 1, we end up with 1/8 minus 1/4. So let's do common denominator 16. So we have 32 minus 1 minus 2 plus 4 over 16. So it is 33 over 16. So again, try to remember this pattern. You will see it on the homework at least a few times. So just remember that minus 1/2 plus 1 turns into positive 1/2, which is exactly the same thing, but with the opposite sign. Now, similarly, we can change the direction in which we integrate. That is, if you have a function defined as x being a function of y, so you may have a curve like this, and you want to know the arc length of this curve, you can find it by setting up this integral. Let's do a problem. I'm going to give you another problem to exploit that same pattern as before. So step 1, find the derivative. Step 2, square. And notice how the middle part becomes negative 1/2. So that means when we add 1, we're going to end up with the same exact thing, but with plus 1/2 in the middle. And when we take the square root, this will become, yes, we can write it here. And since y is positive, we don't have to worry about the issues with the signs, so we can just remove the square in the radical. And now we're ready to set up the integral. We're going to have an integral from 1 to 4 of y to the power 1/2 plus 1/4 y to the power -1/2 and 2/3 y to the power 3/2 plus 1/2 y to the power 1/2 and so we have 14/3 plus 1/2, which is 31/6, which is the arc length of this curve. Now, to wrap this up, I would like to introduce the following function. So for some given f of x, which is defined on the interval from a to b, let's consider the function sx that looks like this. So what this function does is so this is f of x, this is a, this is b, sorry, this is not f of x, this is f of t, and x is just some number between a and b. And what s of x does, s of x tells us the length of this segment, or arc length. And s of x, therefore, is called the arc length function. And as a function, just like any other function, it has a derivative, and its derivative will be written like this. This is in Newton notation, and in Leibniz notation, it will look like this. Here we'll write dy. And the idea is that we want to be able to kind of imagine the following picture when talking about arc length. We're gonna have dx, dy, and ds, which naturally form a right triangle, and ds in here is equal to this. As a differential, it is equal to this, and if we kind of manipulate this expression like this, which kind of, it again, visually it makes sense, mathematically it doesn't make sense. However, at the end it ends up making sense, which is interesting. What we did here, so this mathematically makes no sense. But if visually we treat this as a variable and distribute this inside of the radical, then we're going to end up with something like this. Which again, mathematically, we still have to be more careful here, but visually it does make sense. And we can then square both sides, and then this looks just like the Pythagorean theorem. So like I said, visually it does make sense. Symbolically it almost makes sense, but mathematically this is, we're not quite sure what's going on here. Like, I mean, it's not clear what does this mean. However, visually, just visually and symbolically, we can now remember the following, like create the following two relations. So on the one hand, ds can be expressed like this. On the other hand, ds can be expressed like this, just by manipulating this expression symbolically. But now this actually has a very powerful application, or not the application maybe, but the purpose. Instead of trying to remember two arc length formulas, one for x, one for y, we can now create a single arc length formula that looks like this. And here we're just going to integrate over the appropriate domain. And this is the only formula that one needs to remember if all of these manipulations are understood. So in this formula, ds stands for this, and therefore, depending on the problem, can be interpreted either like this, which then becomes our formula for the arc length when the function is given as y being f of x, or ds sometimes can be interpreted like this. And this gives us this formula for finding the arc length when a function given as x being g of y. So in summary, we learned how to find the arc length, And we created this universal arc length formula that allows us to find the arc length of a function regardless of how it is defined.